Guys, welcome back to the structures and functions of biomolecule course. Today is our fourth lesson, and we are bringing to you carbohydrates. So we want to study carbohydrates, and before we can study carbohydrates, we have to know some basic terminologies before we can study carbohydrates into very details. Alright, so today we are going to study those terminologies one by one and know what each of them means, so that our next video will tackle carbohydrates and it will be very easy for us to move at a faster pace. Alright, so we are going to talk about key terminologies in the study of carbohydrates. Okay, alright, so our learning objectives are going to be anomers. So we are going to talk about what anomers are. Alright, so we're going to talk about epimers, mutual rotation, penultimate carbon, glycosidic bonds, hemiacetal and acetal links, hemiketals and ketal bonds, Howard projection, Fischer projection. Okay, so we are going to talk about all these things into details and tell what each of them are. So our last video we talked about stereoisomerism, and we talked about enantiomers, we talked about diastereomers, meso compounds, and the rest. Okay, so in the study of carbohydrates, they all apply. All right, so we are continuing with these terms so that carbohydrates will be very easy for us. Okay, so in studying carbohydrates, we need to include stereoisomerism. Okay, we need to know optical activities, we need to know chiral centers, as we studied in the previous lesson. That's lesson 3. So if you've not studied lesson 3, you can just check in the description below and you can find the link to lesson 3, so that you can go back and read and learn before you can able to acquaint yourself with this new topic. Okay, so we are going to talk about anomers, epimers, mutual rotation, penultimate carbon, glycosidic bonds, hemiacetals, hemiketals, Howard projection, and Fischer projections. Okay, so I don't know, you guys studied Fischer projection in organic chemistry, and we will be doing it here. So if you've not even studied Fischer projection in organic chemistry, we are going to learn it over here, so you'll be able to get it very well. Okay, so let's start with Fischer and Howard projection. Okay, so a Fischer projection is just a representation of a sugar in their open chain form. Okay, so when you have a sugar molecule, in the representation of this sugar molecule in their open chain form is what we call a Fischer projection. Okay, so for a sugar we have 6 carbons. So we have the first carbon here, the second carbon, the third carbon, the fourth carbon, the fifth carbon, and the sixth carbon. Okay, so these carbons are arranged in their open chain form. Okay, and this is called a Fischer projection. So this is how a Fischer projection looks like. Okay, and remember we talked about chiral centers and chiral molecules in our last video, as I was saying. So in this compound we can determine some chiral centers here. We can see that the carbon 2 is a chiral center. We can also see that carbon 5 is a chiral center, and carbon 4 is a chiral center, and carbon 3 is also a chiral center. Okay, so that's chiral centers for you. And if you don't know how to determine chiral centers, as I said earlier, you can go into the description and learn how to identify chiral centers. Okay, alright, so this is a Fischer projection for you, and this is a Howard projection. Okay, so Howard projection are often used to depict sugars in their cyclic forms. Okay, so as we have this sugar here, this is called glucose, D-glucose. Okay, D-glucose, and in no time you will learn why this is called a D-glucose and L-glucose. So we have enantiomers. All right, yes, so as I said earlier, carbohydrates, we need to know enantiomers, we need to know diastereomers and meso compounds. Okay, so we have enantiomers of glucose. So the first one is D-glucose, and we have L-glucose. So we will study them later and you get to know them. All right, so this is a cyclic form of a sugar, and it is called a Howard projection. Okay, so these 6 carbons are represented in a cyclic ring. All right, so as you can see, we have carbon 1 here, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. All right, and we have this bond over here. Okay, so we will talk about this also in the meantime. This is a linkage. Okay, so it's a linkage, and we will determine how this linkage is formed over here. So it's between the penultimate carbon and the functional group of the other glucose. So that's how it will be forming. All right, so we have this functional group here, aldehyde functional group, and we have an OH here. So there is going to be a bond linkage between these two groups to form this linkage over here. All right, so we'll talk about it in the next slide. Okay, so our next terminology here is anomers. All right, anomer. So when we talk about anomers, they are diastereomers of cyclic forms of sugar or similar molecules differing in configuration at the anomeric carbon. That's carbon 1 of a sugar, an aldose sugar, or carbon 2 of a 2 ketose. All right, a ketose sugar. Okay, so when we talk about anomer in the simplest form, we have an alpha anomer and we have a beta anomer. So the cyclic form of carbohydrates can exist in 2 forms. So we have the alpha form and the beta form. Okay, and these are based on the position of the substituent at the anomeric center. Okay, so when we talk about the anomeric carbon is the carbon 1. All right, a carbon 1 of any sugar represented in the Howard projection. Okay, so this is the Fischer projection and this is the Howard projection. So carbon 1 here is called an anomeric carbon. Okay, so it's called an anomeric carbon, and this is also called anomeric carbon. And why do we have alpha D glucose and beta D glucose? So it's due to the position of the hydroxy group, the OH group at the anomeric carbon. So the position where it shows the direction determines either it's alpha or it's beta. Okay, so when the hydroxy group is in opposite direction to this functional group over here, the CH2OH. Okay, that's the ethoxy group. All right, then we have an alpha D glucose. Okay, and we have an alpha D. Okay, so when we have the hydroxy group in the same direction as the carbon 6 over here, then they are in the same direction, and therefore we have a beta glucose. Okay, so that's the anomers for you in the representation of a sugar in cyclic form. So these anomers can only be determined when sugars are in their cyclic forms. All right, they cannot be determined in their Fischer projection. We can't deduce whether this glucose is in the alpha form or a beta form. All right, since it's in the Fischer projection. So unless we convert it into a Howard projection, all right, and in order to convert this into Howard projection, there is a reaction, okay, between the functional group, aldehyde functional group here, and the OH here. Okay, so there is a loss of water between these two molecules. So there is H2O. So we have 2 hydrogens here and we have 2 oxygens here. So when there is H2O, that means 2 hydrogens are lost and 1 oxygen remains. So this is the 1 oxygen that is remain, and it forms a bond that joins carbon 5 and carbon 1 together. So there comes, we have an anomer. All right, so these are the basic terminologies, and this is anomer for you. Okay, so our next term is epimers. Okay, so when we talk about an epimer, when sugars differ from one another in configuration at only one chiral center, they are called epimers. So for instance, let's say we have galactose here and we have glucose. All right, we have D-glucose here, we have D-galactose, D-galactose and D-glucose. All right, so for example, glucose and mannose are epimers at carbon 2. Similarly, glucose and galactose are epimers of carbon 4. So let's consider these sugar molecules. So we have D-galactose here and we have D-glucose here. So the basic definition of an epimer is that the two sugars should differ at one chiral center. Okay, only one chiral center. Only one chiral center. So let's check galactose. When we check at carbon 1, we have a double bond then to oxygen here. We have a hydrogen here. We have a double bond to oxygen. That's the functional group of an aldehyde. Okay. When we come to carbon 2, we have hydrogen here, OH here. We have a hydrogen here, OH here. So they are the same. They are the same positions. Okay. When we come to carbon 3, we have HO here, HO here, hydrogen, hydrogen. So it's the same direction. So when we come to carbon 4, we have hydroxy group here, we have hydrogen here. So there were supposed to be hydroxy group and the hydrogen over here, but in this case the position has been interchanged, so the chiral centers has been changed. Okay, so has been a change in their configuration, so it can be either R or S. So the change in sugars at only one chiral center is called an epimer. So when we take galactose and D-glucose, they are epimers at carbon 4. Okay, so it can come in your exams and they'll ask you determine which of the following sugars are epimers. All right, anomers and other stuff. So what you have to do is that in order to determine whether two sugar molecules are epimers, they are supposed to differ at one chiral center. So considering D-galactose and D-glucose, we can see here that they change in position. All right, so there is a change in position between this hydroxy group and hydrogen. Okay, so we have hydrogen here, we have hydroxy group here, so they have been swapped, so they can be termed as what? An epimers. So now let's compare D-glucose and D-mannose. We can also see that at carbon 2 there is a change in position between hydroxy group, which were supposed to be here, to here, so it can also be termed as what? An epimer. Okay, so that's the basic definition of an epimer. Okay, so let's continue with penultimate carbon. So when we talk about the word penultimate, it means last but one, or second to last carbon. So last but one or second to last. Okay, so the penultimate carbon in a sugar molecule represented in a Fischer projection is the last chiral carbon of the chain. Okay, so when you check D-glucose over here, we have carbon 1, 2, 3, 4, 5, 6. So the penultimate carbon is carbon 5. That's the last but one carbon. All right, and it's the last chiral carbon in the glucose molecule. Okay, so the alcohol group attached to this carbon is that which attacks the carbonyl group during cyclization of sugar. So as I said earlier, this is the cyclization reaction, and this leads to the formation of a Howard projection. Okay, so in order to convert Fischer projection to a Howard projection, there has to be a cyclization reaction, and this cyclization reaction is a reaction between the OH group at the penultimate carbon and the functional group of the aldehyde. Okay, so that there will be a loss of water in order to form that a bond between the glucose. Okay, so there is supposed to be a loss of water in order to form the cyclic sugar. All right, so this is the penultimate carbon at carbon 5 for D-glucose and the penultimate carbon for L-glucose. Okay, so this glucose, the L-glucose and the D-glucose, is just an enantiomer. All right, so when we talk about an enantiomer, it's just the mirror image. So it's the mirror image of each other. So when we check, we have OH here, OH here, OH here, OH here, hydrogen, hydrogen, OH, OH. So it's a mirror image of each other. So it can be termed as an enantiomer. All right, so that's the basic term for penultimate carbon. So that's what it means. It's the last but one carbon or the fifth carbon in a sugar molecule that is represented in a Fischer projection, to be precise. Okay, sure. Okay, so we are going to talk about glycosidic bond. Okay, so what is a glycosidic bond? So a glycosidic bond or a glycosidic linkage is a type of a covalent bond that joins carbohydrates or a sugar molecules to another group, okay, which may or may not be another carbohydrate. So it can be the same carbohydrate. It can be a glucose, a glucose galactose, a glucose mannose, a glucose ribose, or a glucose galactose. All right, so it can be any sugar molecule. So a glycosidic bond is a type of bond, a covalent bond that is formed between two sugars. Okay, so this is a glycosidic bond between two alpha D glucose. Okay, so a glucose and a glucose is called maltose. All right, so we have an alpha D glucose over here, and the reason why it is alpha is that it's opposite to the group, the carbon 6 over here. All right, so it's opposite in direction, and this is in the same, this is also in opposite direction, so they are all alpha groups. All right, sure, so they can be termed as alpha D glucose, and this is the glycosidic bond. So it's a bond, a covalent bond between two sugar molecules, and it is formed by the hydroxy group. So the two hydroxy group will also form a bond, and there will be a loss of water, there will be a loss of H2, so it will form this glycosidic bond. All right, and this glycosidic bond is a covalent bond. So for example, let's also consider lactose over here. So when we talk about lactose, we have a galactose and a glucose that forms lactose. So we have beta D galactose, and the reason why it is beta is that it is in the same direction, the hydroxy group is in the same direction as the carbon 6 over here, and the reason why it is a D glucose is that it's the first the enantiomer of lactose, and it's in the D direction, that's the right direction. Okay, so when you convert this cyclic sugar into a Fischer projection, you see that this is in the right direction, that's why it is a beta D galactose. Okay, and this is the glycosidic bond. Okay, so it's a bond between two sugars which leads to a loss of water between the sugar molecules, and it forms a glycosidic bond. All right, sure. So that's glycosidic bond. It's a bond between two sugar molecules. So as you can see here, we have a glucose sugar here and another glucose here. So the definition says which may or may not be another carbohydrate. So it can be the same carbohydrate or it can be another sugar molecule. Okay, so that's glycosidic bond. Okay, so another terminology that we need to pay attention to is mutual rotation. Okay, so when we talk about mutual rotation, we have to make reference to specific rotation. So it's an optical rotation, and we covered that in the third lecture, so you can go back if you haven't read it yet, so that you can know it very well. All right, so when we talk about mutual rotation, it is the change in optical rotation due to change in the equilibrium between two anomers. Okay, so we have alpha anomer, beta anomer, as I said earlier in the previous slide. So when you check this molecule, it's in the same direction as the carbon 6. Okay, so it's a beta D glucopyranose. Okay, so this is epiranoose. Okay, yes, so an equilibrium reaction between this beta molecule can convert this molecule to an alpha D glucopyranose, and this is called a mutual rotation. So it is the interconvertibility between two anomeric forms. So we can convert a beta D glucopyranose to an alpha D glucopyranose, and this is called a mutual rotation. So cyclic sugars show mutual rotation as alpha and beta anomeric forms interconvert. So when we change a beta D glucose to when we meter rotate it, that means we are changing the beta D glucopyranose to an alpha D glucopyranose. Okay, yeah. So that's the basic terminology of meter rotation. So we are meter rotating it. So we are changing the configuration. So when we are changing the anomeric form. So if it's in the beta anomer form, then we are converting it to what? An alpha anomer form. Okay. Alright, so another word that we have to know before we can study carbohydrates without any difficulties is ketal, acetal, and hemiacetal, and we also have ketal and hemiketal links. Okay, so hemiacetal or a hemiacetal is a compound that results from an addition of an alcohol to an aldehyde. Okay, so when we add an alcohol to an aldehyde, that means we are breaking the alcohol, the carbonyl functional group over here, and we are adding an OH group to this aldehyde. Okay, so we are adding an OH. Okay, OR, that's the alkyl group, to this form. All right, so when we add the OH, the hydroxy group, to this form, we are going to form a hemiacetal. So in short, it contains one hydroxy group bonded to the central atom. So we have one OH group bonded to a central atom. So it's a tetrahedral carbon. A tetrahedral carbon means it's having 4 bonds. Alright. Okay, so we have the one bond here, which is the R. We have a hydrogen bond here. We have an alkoxy bond here, and we have a hydroxy bond here. Okay, so it's a tetrahedral carbon. So a tetrahedral carbon with one hydroxy group is a hemiacetal. Okay, so we use it in the study of carbohydrates. Okay, so it's very, very important that you need to pay attention to, sure, so that maybe you will not be confused when you meet these terms. Okay, and this also can be converted to an acetal by adding another OH group. Okay, so when we add this ROH, then we are converting this acetal to acetal, this hemiacetal to acetal. That means we are removing the OH group and we are adding R group, okay, to it, and it will convert the hemi to acetal. And in the acetal is also a tetrahedral carbon, but there is no hydroxy group. There is no hydroxy group. It's only alkoxy groups. Okay, alkoxy groups is a methoxy group. That's it's methanol. Okay, so it's a methanol. Okay, so it's an alkoxy group. So the acetals are tetrahedral compounds where 2 alkoxy groups, so OR groups, are bonded to the central atom. So in order to differentiate hemiacetal from acetal group, so for the hemiacetal we have one OH group and one alkoxy group, so one hydroxy group and one alkoxy group. But for acetal we have 2 alkoxy groups with no hydroxy group. So that's the difference between a hemiacetal and a hemiacetal and an acetal bonds. All right, okay, so we are going to talk about a hemiketal and a ketal. So as we said earlier in the hemiacetal and acetal, we are also going to talk about hemiketals and ketals. So the hemiacetal is for aldehydes. Okay, so in order to convert aldehydes to acetals, that means we are using an aldehyde. Okay, so in order to get hemiacetal groups or acetal groups, we have to use aldehyde. And in order to get a ketal group or a hemiketal group, we have to use a ketone. So when we convert a ketone, okay, to a hydroxy, we add one hydroxy group to a ketone functional groups, we convert it to a hemiketal group. So a hemiketal is a compound that results from the addition of an alcohol to a ketone. Alright, so when we add this alcohol to this ketone, we are adding one OH group to the ketone functional group. So we are going to get a hemi. A hemi means it's just half. So we are adding only one hydroxy group to this ketone. So we get hemiketal, as in the case of aldehyde. So when we add one hydroxy group to an aldehyde, we get hemiacetal, which is acetaldehyde. So it's an aldehyde. So in case of ketone, we get hemiketal for the first reaction. Okay, and in the ketal, we have a functional group derived from the ketone by just replacing the carbonyl functional group by two alkoxy groups. So we add two alkoxy groups, so two RO groups, that's OR groups, to this ketone. So with that case, we are converting the OH over here also to OR groups. So it's the same as converting the aldehyde to an acetal. It's the same way as also converting a ketone into a ketal. Okay, so ketal and acetals have the same reactions. Okay, so it's just addition of two alkoxy groups to a ketone to get a ketal group and an aldehyde to get acetal groups. Okay, so that's these definitions that you have to pay attention to. Okay, so it's very, very important before we can study carbohydrates. You have to know these very basic definitions, which anomers, we have epimers, we have mutual rotation, we have hemiketal, ketals, and epimers. You have to know all these definitions. And don't forget about enantiomers, diastereomers, meso compounds. Okay, so because they are all going to help you to identify whether a specific sugar molecule is an enantiomer of the other, is an epimer, is an anomer, or any other molecule. And also don't forget the glycosidic bonds, how to convert a Fischer projection also to a Howard projection. All right, so this is the end of the fourth lesson. And the fifth lesson, we are going to talk about carbohydrates into detail. So we are going to apply these basic definitions. All right, so these basic definitions are going to help us to study carbohydrates without finding any difficulties. Okay, so if you don't understand the enantiomers, diastereomers, stereoisomers, and the meso compound, just go back to our third lesson, or you can find it in the description so that you'll be able to guide yourself through the course. Okay, so we are just following it in order as a structure and function of biomolecules course. All right, so have a nice day and try to solve many questions on this so that you won't find many difficulties. You can find molecules and try to identify the chiral centers, try to identify whether they are ketals, try to identify whether they are hemiketals, try to identify whether two sugar molecules are epimers of one another, they are anomers of one another, or others. All right, so try these basic terminologies and make sure you understand them very well before we study carbohydrate. All right, and don't forget to subscribe to this channel or like and make comments. So if you have any question, you can just go to the comment section and you can type it over there, and we will reply you as soon as possible to prevent any difficulties. All right, so have a nice day and hit the subscribe button over here for us so that you get notified when any video comes. All right, thank you very, very much.